You can do it space.
You don't want to share screen.
That's
where it gets, I was using that thing there, the yellow button. Oh yeah, there it is. That's fine. Yeah,
Blue star.
yeah. That's
Oh, wait a minute, no, I didn't share the screen, I didn't share the screen properly. Let me stop, it's not sharing the blue star, I have to share the blue star. Share screen.
that's brilliant.
Okay. You can take it, Lou.
Right, we're ready to start. We realise there are probably problems with the Zoom, but yeah, it's more important work for the people here to carry on, I think. Yeah. Right, so the first speaker is Kauffman, and he's going to talk about topology, algebra, and physics, and its normal operations on the.
And what were you saying
So
about
if you
the
could stand
camera?
up here and just spend about 30 seconds introducing your talk.
Oh, I see. All right.
Are we recording?
So are we're actually broadcasting this?
Yes,
Yes.
This is a physical.
And I should start.
yes, you can start.
And why is everybody sitting?
That is a
30
very
feet away?
good question. They're a bit shy.
You should move up. Yeah.
That's what I think. Yes, come closer. Right. all yours.
And now we're divided even further. Yes.
Yeah,
Yeah.
I'm sorry, I was just trying to, Diane asked me to make the screen bigger. I guess that's good enough.
So this talk is about topology and algebra. You might have heard some of this before, but part of what I'm interested in is from a long time ago, a way of interpreting the quaternions topologically, and then to go from there to a slightly more complicated way of interpreting the octonions topologically. And that part still needs to be thought about further, as you'll see, but it does work. It's a little more complicated than the topological interpretation of the quaternions, which we might as well just begin with right now. So let me think. Yeah, I think I'll just start with that rather than use the slideshow, and then we'll use the slideshow. So the point is that the quaternions can actually be placed directly in your hand. If I take my arm and I point it, I'm going to ask you to do this in a moment, but just you might as well just watch me. I put my hand forward, and I say that I will be a rotation of 180 degrees around the axis going straight out of my body. Okay, that's I. Now, those 180 degree rotations are easy to do with a belt, but they're also easy to do with your hand, at least in one direction. You'll notice that if you put your hand out, you can turn 180 degrees counterclockwise without any trouble, but you'll have a little difficulty turning 180 degrees anti-clockwise. But anyway, I is 180 degrees like that. And why do I say that? Well, I'll come back to why I say that I is a 180 degree turn. But then J is going to be a 180 degree turn around the vertical axis, which I can do if my palm is down 180 degrees around the vertical axis, and I find my arm folded to my shoulder. And J is going to be 180 degrees around the horizontal axis across my body, like that, 180 degree turn. And you'll notice that I followed by J is the same as K. Did I say K? Did I say J? I meant K. Okay, so I, J, and that's the same as K. All right. So that's the beginning of the thing, right? I times J is supposed to be K, according to Hamilton. But then what if you do I times J times K? All right, so you do I, and then you do J, and then you do K, which is a 180 degree turn. And you find that your arm is now pointing straight back out and twisted by 360 degrees. All right, 180, 360. And I claim that that's -1. Okay, the 360 degree twisted arm is -1. And at that point, we should actually go over to topology and take a look at why I'm saying that that should be -1. So if I were to take a belt and we call that holds one end, and we twist this belt by 180, 360 degrees like that. And then you imagine that the belt is actually attached to a sphere hanging in space so that it can go through my arm if I want to. All right. But it's rigidly attached to the sphere, and the sphere is no longer rotating. Then I can do that by exchanging hands if I want to. I have this 360-degree twisted belt, and if I bring this around like that and exchange hands, that's the same as bringing it all the way around the sphere. And in this case, it's still twisted. But if you look, it's twisted clockwise, and I started by twisting it counterclockwise. What's more striking and easier for you to see is that if I were to take this and twist it 360 and then 360 more, so that it's twisted by 720 degrees, and I bring that around the sphere in space, and it all goes away. So think about that for a moment, and let's do it again. The 180-degree twist, which I was doing counterclockwise, so let's do it counterclockwise. One of them, two of them, and that makes for a 360-degree twist. And now I do an entire other three. Could you just put your hand right?
Yeah.
No, right there where I'm
Right
holding.
there.
That's it. Now I'm going to put another 360-degree twist in there. Now, if I take this around the sphere, it becomes an opposite 360-degree twist, which wasn't quite obvious to you when you looked at it, probably, but now we can compare it with the original 360-degree twist, and can you see? They're opposite, and when I let go, it disappears. So that what happens is that if you do it 4 times, you're back to where you started. If you do it twice, and then you do it, and then you square that, you're back to the identity. So one full 360-degree twist done twice is nothing. So one full 360-degree twist formally looks like -1. It's clear?
Yeah.
So therefore, and that would work in any, that would actually work in any direction. Suppose, for example, that I did 180. This is like this one, right? I do a 180-degree twist, another one that's 360. You see, it's building up on the belt. Topologically, it's just twist. Another one and another one. That's 4 of them. And now we have 720 degrees of twist on the belt. And if I pull it around the sphere, it goes away. So it doesn't matter in what direction in space I do that 720-degree twist, it will all go away. Something's bothering you.
And it's just so weird. It's so amazing. I'm just kind of, it's so,
Oh, it is amazing.
yeah.
But on the other hand, it's actually easy to comprehend, right? Because of the fact that if you put a 360-degree twist in the belt, and then you pull it around that sphere and back around, it turns into the negative 360-degree twist. But then what did that have to do with what we were just doing? Maybe I can use this, I don't know. What we were just doing was we were saying in any direction of space, I can twist by 180 degrees. So that means that I'm doing a square root of -1 directionally in that direction. And if I twisted 4 times, it would all go away. I can't with my arm, but I could with the belt, you see. Yeah, I can do exactly the same thing. I do 1, 2, 3, 4, and then this is a 720-degree twisted belt, and up to moving it around the end, which could be done, it will all go away. Right. So what I did with my hand can be done with the belt in this form. That was this, and then J, which was this, and then that's equal to K, which was this. And if we did I and then J, I and then J and then K, then I end up with a 360-degree twisted belt, but 360-degree twisted belt is -1. So the quaternions are right there, between the topology of the rotations of something, a hand, an arm attached to the hand attached to the body is the object attached by some flexible belt to some ground or wall or whatever. So the quaternions are in the palm of your hand in that sense.
I was just guessing, it was what Peter was just saying as well, that you're saying the quaternions are the only way to understand 3D, right? And I was just guessing, because as you know, I've got this thing about the 3-4-5 triangle, which we won't go into now, but the 3-4-5 triangle is like the archetype for the plane. So it's like really, really important for the plane. And I just see that the quaternions are for 3D, so.
Yeah, quaternions are kind of archetypal for
Yeah.
3D in that sense.
Yeah.
And also, if you were to take an object, I don't have a picture, I don't have one, but so imagine that I'm holding, say, an icosahedron, right? So that has a symmetry group. It has an order 60 symmetry group of rotations around different axes of the icosahedron. And there it is in space. But if you attached a belt to it, then when you rotated it by 360 degrees, the icosahedron is back where it was, just like my hand will be when I rotate by 360 degrees. But the belt is twisted by 360 degrees. So it's flagged as a different element in the symmetry of it. And that means that you double the symmetries of the icosahedron up to 120 when you do that. And now what does this have to do with various things? Well, maybe I postpone talking about where that symmetry group is now, but it's in the quaternions in any case, right? That you now have a subgroup of the quaternions, which has a doubled symmetry group related to the symmetry group of the object in three-dimensional space.
What does that mean for implication like Spencer Brown's work and Art Collins, like as far as like rotations and symmetries and identities for self-reference?
You're talking about, I don't know, it started again.
I'm sorry, what I'm asking is, what is that, what are the, when you go back to yourself, when you go back to the identity, what does that, what are the implications for self-referential statements like with Spencer Brown and Art Collins' work using the quaternions and complex numbers and logic?
Yeah, well, Art and I have been working on pushing the quaternions and also the complex numbers into the framework of laws of form. So you're asking, oh, there's no blackboard. Well, let me try just talking about it. If instead of talking about the quaternions, let's just talk about the square root of -1 for a moment.
I've got
So
some big paper and pen if you want.
there is a.
I mean, it's not a blackboard. but I've
Do
got-
we have something to write on?
I'll show you what I've got.
Yeah, there's paper back here.
Chance.
Yeah. I'm just thinking in terms of like, not being getting back to the identity and what is that, the implications for that is.
Yes, I understand. I just, the point is, I don't know if there's something to support this. Otherwise, I wave my hand.
Just looking for.
Maybe we can find something like, oh, that's easier to hold up.
Yeah, that's easy.
Let's try that.
Oh, yeah,
No.
all my stuff in there.
Yeah,
If I take my stuff. Yeah, that's it.
okay,
Change the camera.
Yeah, let's change.
wait, we're still making.
Oh, that is as well. Yeah, but that should stay in. That should
That's
all
okay.
stay in. If you use it that, if you do it that way, right? This is the bottom top.
Well, yeah, but no, I don't want extra sheets that they'll drop as I try.
Oh, I see.
It's better if I just fold it back over.
Okay.
If that's not a loose sheet, then.
Oh, it's got a magnet.
Okay. Then. Okay, so So there are a number of different points of view here, which is why I'm slowing down. I just want to talk about the square root of -1 for a moment. And of course, I was going to say this in a different order, but we're all familiar with, oh, that's no good. Does anybody have a really dark marker? The pen. See, the pen's line is probably invisible to you.
I can
Black
see
pen,
it.
it's still the best one. Got a black pen.
No, I want a magic marker so that there's a reasonable line. If not, I think I'd better just talk this through. So you asked about self-reference. And if you ask about self-reference, perhaps you're asking about the level of language where we refer to ourselves. In which case, it doesn't necessarily look like there's any mathematics going on there. It looks like we're talking about reference, which could turn and refer to the thing that's doing the referring. And if you're thinking about distinctions, then you can find yourself with a formalism that involves self-reference in the most elemental way if it's iconic. So for example, in laws of form, a circle or a mark makes a distinction in the plane and is understood to make a distinction. The marks that we make in written language particularly, and indeed the marks that we make in spoken language in the sense of utterance, they make a distinction in the space in which they're created for us. And so the mark makes a distinction, and the mark is a distinction. And so the mark, my utterance, or the mark that I draw, refers to itself. It refers to itself implicitly. It isn't pointing to itself. But a next level of self-reference is where the entity which is referring to itself actually has a pointer which points to itself, like an arrow that points to itself.
Like identity.
Right. And when we get to that level, it's possible to have something which leads you to think that you're talking about something paradoxical when you're talking about self-reference. Because when you have this gadget which pointed to itself like that, then you were thinking of it as being inside itself. So that if this was the A that was pointing to itself, then it would be pointing to itself inside itself. Which is also a kind of a psychological, what do we have
That's a
here?
little bit thicker.
Another possible
Yeah.
marker.
Bit thicker, not-
So if it's pointing to itself inside itself, then it looks like it's something which is invariant under some operation that has been performed. And indeed, as I say, that's part of the linguistics of it, or part of the understanding that we have, that we point to ourselves, but it isn't exactly to ourselves, and yet it is ourselves. Ourself at the next instant is still regarded as ourself. And so you end up with self-reference in this kind of form. And when you're talking about self-reference in this kind of form, and if the A with the cross over it is supposed to be the negation of A, then you are looking at what seems to be something paradoxical, that the A is equal to the negation of A is paradoxical. And you can arrive at paradoxes in the place where the identification of something becomes tricky, right? becomes on the edge. So for example, the barber who shaves everyone who doesn't shave himself is on the edge, and can neither be identified as an element of as a person in the town who's not a barber, who doesn't shave himself. He's either one or the other, not both or both. Which is he? Is he both or neither? And the same for the elements of the Russell set. So you end up with this kind of ambiguity about on what side are you. And of course, you were starting there if you're thinking about self-reference, because are you the one you're talking about, or are you the one who's being talked about in terms of your own self-reference? So it's paradoxical. You can think of other situations which are paradoxical in a similar way. For example, if I wrote the equation x equals -1/x, then it's exactly analogous to A is equal to A cross, or A is equal to not A. There's no real number that satisfies that equation. If I put a 1 in there, I get a -1, and if I put in a -1, I get a 1. And so we could say x is equal to plus or minus 1, but which is it?
Yeah.
And on the other hand, if I wrote it the other way using the arithmetic, I get x squared equals -1, and we can say x is equal to the square root of -1. We can say x is equal to I, and I become I, which is that 180-degree turn. 4 of them give you +1, corresponds to self-reference in that way, right? Now, if you didn't use numbers, you could still ask for what the heck would it look like at the level of form or elementary logic to have something whose square was negation.
Symmetries.
So you can ask, well, what would it be like to have a square root of -1, a square root of negation instead of a square root of -1? What would that be like? Right? And by this line of thought, it would be analogous to having self-reference, but not quite immediately if you're thinking of it the way we were just thinking of it. It's somebody whose square is negation. It isn't obviously self-referential, but if you think of it this way, then you can see how it could be self-referential. And you can also see how to make it because of Hamilton. Remember, Hamilton said that you could think of I in the Hamilton and Gauss. I'm sorry. Suppose that I take the idea of complex number as you well know it, as A plus BI. And then you're thinking of a complex number which is living in the plane like this at coordinates A and B. And I'm thinking of that as a pair, AB, like that, right? Then what happens when you multiply it by I? Well, you all know, I'm just repeating it, but let's multiply it by I. Then we multiply A plus BI times I, and we get IA, and we get BI squared, which is -B. So it's -B plus IA. But then on the level of couples, it says that you take I times the pair AB, and you get -B comma A, right? -B comma A. So you reverse the order and you put a negation sign on one of them, and that's taking the vector AB and rotating it by 90 degrees to get -BA. Take the dot product, for example, and you get 0 between AB and -BA, right? So rotated it by 90 degrees. So multiplying I by any vector rotates it by 90 degrees, a fact that everybody ought to know when they learn complex numbers, but don't necessarily. But the point is that that's the formality of it, right? That's just the formality of it. So if you were taking pairs of marks, you could define an operator on pairs of marks, X, Y, by taking the same thing. You could say that AB operated on by the I mark will be equal to B cross A, where B cross is the usual negation, the usual crossing. All right. Now, what happens if I do it twice? I get A cross B cross, right? It'll rotate one more time and get a negation sign one more time. I squared is -1. But I squared, so then you see that this mark applied to itself will be equal to the negation. So that's the square root of negation. Now we're talking about topology here. So I want to go a little further in this direction. But we can make a square root of negation that way. Now here's the story. I was thinking about that kind of square root of negation years ago. And then Art came to me a few years ago, and he said, I've got this generalization of laws of form that I'm thinking about, where I have a new mark, let's call it cross sub I, whose square, he didn't call it cross sub I, just called it whatever he called it, whose, when you do it twice, you get the mark. So it's an order 4 mark instead of an order 2 mark. And I'm working on this. And then we started thinking about it. Then I said, well, maybe it's like the square root of negation, this one. And we checked, and all his properties, all the axioms that he was working on for his order 4 mark are exactly what's modeled here by taking the pair and rotating it by 90 degrees in that way. So then we started working together on it. But that's one way of thinking about how the complex numbers live down at the level of form. But if you were to walk up to it and say, in what way are you like self-reference? Then you need to think about how is going all the way around 4 times related to self-reference, which is interesting to think of it that way. You get back to self by going around 4 times like that. But then, as I said, we're thinking about topology, so I might as well show you something else about this.
You want to move back a little bit?
Sorry?
You want to move back a little bit so you get it on.
I'm sorry.
We're not getting this on your camera. If you want to.
I don't know. I don't know how to do that.
No, just move back.
I can try
So,
backing up a little bit.
right,
Yeah.
just a little.
So I want to draw a diagram. So now I'm drawing a little bit of weave. 2 lines weaving across one another like this. And the one that goes under is going to get crossed. And the one that goes over is not going to get crossed. Okay. You can see that. So you see that that I'm representing iconically in this case. Crossing will mean that one line goes under another. When that line goes under the other one, it ends up as the cross of that. Everybody should be familiar, I hope you're familiar, with the 2 bits of formalism from laws of form that I'm using here. And those are that if you do the cross twice, just like negation, it's the same as doing nothing at all. And if you do 2 crosses next to one another, that's like saying something twice, and it's the same as saying it once. I call your name twice, the same as saying it once. Or A is A. All right. So in this form, crossing is represented by crossing under, and when you cross over, you don't change. And now what I claim is that this is topological. This is, of course, I, right? This is I in 2 lines, right? This is the I operation. I times AB is B cross A, or not BA, right? All of this sort of thing is almost obvious to us because we're so used to it. I mean, like I times AB is minus B comma A. But if you cast your mind back into Hamilton's time, That was one of Hamilton's big discoveries, that he could think of I operating on couples, pairs, AB, as interchanging them and putting a minus sign on one of them. That made it completely clear to Hamilton and many other people that I was not some weird visitor from who knows where, but simply a mathematical operation on pairs, and probably enabled him to start thinking about quaternions as well. But anyway, I want to show you about what will happen to braiding. Now, in braiding, I can have this. Now, this is a loose braiding. As you can see, it's not woven exactly. A less loose braiding would be this one here. Where I'm braiding in such a way that this one's over and that, and it's under, and then it's over, and I could keep on doing that and make a braid out of 3 strands, right? But this one's a loose braiding, and it can slide back and forth a little bit over there. And so, in fact, topologically, this braiding that I just drew is the same as this one. Like that. Is this visible? I hope this is visible far away. But there's an overline which goes all the way down, and that overline could be shifted back and forth a little bit. And so you get, on the one side, you get braid the first 2 strands, then braid the second 2 strands, then braid the first 2 strands. But on the other side, you get braid the second 2 strands, then braid the first 2 strands, then braid the second 2 strands. And they're the same as long as the braidings are like this. They will slide back and forth. Whereas in the weave, it doesn't slide, and we would expect this weave and the other weave to be different from one another. But in this case, these weaves are the same. And so if my placed square root of -1 braid, if this one really is topological in this sense, then it ought to give the same results for the 2 sides of this. So we can try it out. We could put an A here and a B here and a C here, A, B, and C being either marked or unmarked. And then we watch what happens to them. And in this case, the A goes all the way down and becomes an A. In this case, we get B cross, and then it went over. So this is B cross. And what about this one? This one is C double cross, right? Okay, that's fine. C double cross. Now on the other side, I have A, B, and C. And I have A going all the way down. And I have B cross. And I also have C double cross. So they are the same. They're the same. So these 2 braidings are the same. On the other hand, what would happen if you had some non-trivial braiding like this? Here's the simplest non-trivial braiding. A little bit of weave like that, a weave and then the opposite weave. What will happen to that? Well, the A goes down and becomes A cross, and the B goes down and becomes B cross, and this is equal to the pair crossed, right? This is I squared is -1. And it's not the same as where we started. So this is exactly like in the belt trick. When you did the 360-degree twist, you got to -1. You didn't get to the identity. So that's the way it should be. And on the other hand, if we did it in the way that will pull apart, then you would have A and B here, and you'd have A coming down, and you'd have B double cross. And that's where we need B double cross should be equal to B. Then this will pull apart, and we're good. So what this says is that if you take the I, it's very similar to the quaternions, but it's not the quaternions. If you take any number of braid strands and then any pair of adjacent braid strands twisted is an I, a lot of different eyes going all the way down the line, and they all braid one another. They all act according to the rule for the braiding. So we say that there's a representation of the braid group there. And that's the simplest representation of the braid group that I know, coming from the square root of -1. So now I'm not answering.
There is a braid group?
There is a group of braids.
You mean there's a mathematical group?
Yes.
Braid?
Right, I'd better explain to you why I say group. Suppose I take a braid. Let's take a nice woven braid. Like this one. All right.
Well,
Now I can take another one and multiply by it. So I'm going to take another braid. Maybe I'll take this one. So here's one braid and here's another braid. I drew them one over the others so I could connect them up, but it's just a couple of braids. So a braid means that I have some starting points and some ending points, and then I have some bits of rope that are going, strings that are going down and winding around one another like that, always going down. That's okay, right?
Yeah.
That's what I mean by braid. And I have the same number of points at the top and at the bottom, 3 in this case. And then I can connect up one braid with the other by taking the bottom strands of one and connecting them with the top strands of the other, and I get a product. So given 2 braids, I have a new braid, which is the product of the 2 obtained by attaching the lower strands of one to the upper strands of the other.
What you really.
So that doesn't tell you it's a group yet, just tells you have something algebraic, you can form products. Now, what is necessary for having a group? Well, a couple of things. One is that the product should be associative. It shouldn't matter if I write X, Y, and then Z, that should be equal to X times Y, Z. That's one thing you want for a group, mathematical group. So it just shouldn't be anything weird about the product in terms of in the order in which you connect things up. And topologically, this one's okay that way. Don't worry about that one. But the other one that we need is that if there is an X, then there should be an X inverse so that you get back to an identity. And what is the identity? In the case of 3-strand braids, the identity is obviously 3 strands that don't weave at all. 3 strands that don't weave at all. If you added that on to the bottom or the top, it won't change anything. Okay, so there is an identity, but how do you know that any given braid can be undone by some other braid?
You need an invert.
Well, let's see. Take the one I started with. So I want to multiply this by somebody that will undo it.
Well, the same thing upside down.
Well, down at the bottom, I can take this and do the opposite one. That would get me started, wouldn't it? Because the one I just drew below the line will cancel the one just above the line, right? These 2 will cancel, left and right.
Yes.
Clear?
Yes.
But once that's done, then I could write one here that would cancel this one, and that would be this one. And then once that's done, then I'm over here and I need to cancel this one, which I can cancel this way. And now the product of these 2 braids is equal to the identity. You see, they're just undoing one another. These undo, and then these undo, and then these undo. But in fact, if you look at what I wrote, it is the mirror image of this one, as though this one was standing at the edge of a pond, and the one below is the mirror image that's seen in the pond.
So
Did I puzzle you with this?
No, it's
No,
obvious.
okay,
It's obvious.
right. So that's why the braids are a group. You can multiply any two of them and get another braid. And given any given braid, there's always another braid that will undo it completely.
So as a mathematician, you must see invariance in these concepts in every.
Sorry.
As a mathematician, you must see these concepts and in groups, invariance, all these mathematical concepts in almost everything you look at.
Yeah, groups are ubiquitous in mathematics. I'm sorry, I wanted one more item here. There it is. You might think, but groups are not completely ubiquitous. That's the reason for the item. For example, you might think, well, all right, so there should be a group of knots as well. There should be, given a knot that I tie in a rope, there should be another knot that will cancel this knot out. But there isn't. You can try it. That's a nice experiment. Take a bit of rope and then try to find a knot which would cancel this knot. You know, maybe you think, well, maybe just another trefoil knot will do it. So I have two knots on the rope here. And then I try to get them to interact in such a way that they will do each other in and cancel out. And it won't happen. It just doesn't happen. And in fact, you can prove that if you have a knot, if you have a topologically non-trivial knot, then no other knot can cancel it that way. On the other hand, what we've been looking at just now for braid cancellation is the same as twist cancellation, but it generalized to more strands. If I have a twist like this, then I can cancel it with an opposite twist like that. These two twists will cancel each other out. And if you have, and braids are sort of generalized twists with many, many more lines like this, and a braid, for example, in 4 lines like that, however I braid it, can be canceled by another braid. So then continuing this for a moment, I still got the, yeah, continuing this for a moment. We could go back to that laws of form braiding and wonder about the weave. I just hijacked my talk by your question into a different talk, but it's all right. I like this line of association. So what will happen with this weave if I start measuring it by the square root of -1 laws of form thing, right? What will happen to it? Well, I'll have an A here and a B here and a C here. And I get A going down and getting crossed once, and B goes crossed once, and C gets crossed once. Well, that's interesting. Well, what will happen if I took somebody else which ought to be different from it, like this one? Because this is not the braiding relation, right? Here I have something, another actual weave, somewhat similar to the other one. But these are obviously not equivalent to one another. We should prove that there's no way to get from this braid to that braid. But what happens here is that I get C cross, I get A cross, and I get B cross in the center. And so I get the same thing. So it doesn't detect that. It detects some things, but it doesn't detect that. So you might wonder, well, what conceivably could detect something like that? You're going to need something different. So I want to show you something that is kind of amazing. And yet on the other hand, well, I'll do it in the form in which it's kind of amazing, and then I'll explain why I don't think it's so amazing. Suppose you're imagining creating universes algebraically. And I mean mathematicians' universes, they don't have to be physical universes. But I'm thinking of entities that can interact, right? So in laws of form, you have the interaction of an entity with itself gives nothing. Or from nothing comes 2 copies of the entity that are polar different from one another. One's inside the other, right? So that's a very elementary kind of universe, the universe of one distinction. But you could try to think about universes with more entities in them. So suppose I have a universe with two entities in it, and they're allowed to interact to produce a third entity, different from either of them. Then what kind of an algebra could you describe for such a universe? If the third one that was created could then interact with the first one or the second one and produce even another one, we'd be off into a more complex universe. So the simplest universe that I can imagine with three entities, A, B, and C, would be that A interacts with B to produce C, but B and C interact to produce A, and C and A interact to produce B. That's the simplest closed universe with three entities that I can think of. What?
I'm thinking of a quaternion.
I'm sorry.
I'm thinking of a quaternion system.
Yeah, maybe a little like quaternions, but I don't have any signs yet. Okay. So I'm going to have that A and B interact to produce C, and B and C interact to produce A, and C and A interact to produce B. And furthermore, it's very simple, so it doesn't matter in the order in which they occur. AB equals BA, and so on. And then you realize, well, but for a closed universe, I have some choices about how something could interact with itself. In laws of form, there were two choices. One choice was the mark next to the mark produces the mark. And the other choice was the mark interacts with the mark to cancel it out to nothing. So from nothing comes a mark. So we could choose one of those, and let's, for the sake of this one, choose that A interacts with A to produce A, and that B interacts with B to produce B, and that C interacts with C to produce C. All right. So that's a very simple three-entity universe. Each one interacts with itself to produce itself, and each one interacts with the other to produce the third. And it's a discrimination universe as well, right? Because if you had someone and another one, and you let them interact, and you got one of them back, then you know that they really weren't different.
Right. Yeah.
But if you interacted them and got somebody new, then you knew they were different. So this is an elementary discrimination among three things universe. It's like laws of form, but it's, if you want to try to write it as an extension of laws of form, you could. But the point is that as you start building, as you well know, as you start building algebraic possibilities, then you get all sorts of things coming out. So I'm going to try this one out on the braiding. So how could I do that? Well, I'm going to do that in the following way. I'm going to have an X here, and I'm going to have a Y labeling the line, just as I did before. So this line is labeled Y, and this line is labeled X. And now I'm going to have their interaction here. So before, an upper line, I wasn't using its label. I was just saying when you crossed under it, you crossed. But here, it's more equitable. They have a label, and the label tells you what happens when you go through. So if you have an A line and a B line, then this would be a C line. And then you see that there are a couple of possibilities here. You could have A and B, and then you would get C, or you could have A, and you'd get A. And the same for permuting the letters. So if a thing interacts with itself, it produces itself, but if it interacts with somebody else, it produces the third. So now what will happen? Well, will this behave well with regard to braiding? It isn't obvious, right? We made it up as an elementary universe involving three entities, or an elementary discrimination. So let's try it out on the braiding. Of course, there's a number of things to try. I just decided to use starting values of A, B, and C. And now can you do it in your hand? Oh, well, we've got to do the other one as well and compare them. Okay. So now there's the exercise we have to do. We have to compute down both of these sides and see whether they came out the same or not. So let's see. A comes down. B turns into an A. B interacts with A and turns into C. And C interacts with A to produce B. And B interacts with C to produce A. Okay. Oop. Okay. Now over here, A comes all the way down. A came all the way down. B interacted with A to produce C. And C interacted with B to produce A here. And then A interacted with A to produce A. And it worked. And now you see that choice that I made about A interacting with A to produce A rather than nothing or something else was a good choice. It really works. It braids correctly. And on the other hand, what about this one? Here's an A and here's a B. Somehow when I'm drawing upside down, I want to draw the A differently. A comes all the way down. B interacts with A to produce C, and C interacts with A to produce B again. And that's good because if I pulled them apart, then this would be A all the way down to the bottom, and that would be B all the way down to the bottom, right? So this works. This produces something which will always give the same answer no matter what braid you used. But now what about the weave? The weave we were worrying about. Okay, so there are the two weaves that I wanted to compare here. And A interacts with C to produce B. C interacts with what? B interacts with A to produce C. C interacts with C to produce C. C comes on down. On the other hand, A interacts with C to produce B. And that comes on down here. B interacts with B to produce B. And C interacts with B to produce A. And they're not equal. And that is showing you that these two weaves are actually different. So what I neglected to tell you was that two braids turn out to be topologically equivalent to one another if that slippery weave is allowed to be used. And of course, canceling things that are like this is allowed. It turns out that's enough to describe what it means for two braids to be topologically the same. So if we have something that doesn't change under those two, then there couldn't be any way to get from here to here because it wouldn't change under those two, but this does change. So this simple three-element algebra tells you a lot more about the weaves than the laws of form one did. And so you're propelled into looking for possible universes of algebraic universes that can discriminate topological things like that. So that takes you into another level of trying to generate appropriate algebra or appropriate discrimination. Because you can say, well, what is it that I'm actually needing in order to do this? So if I had a system that was like the one with 3, but I didn't know that it was that, I just had some way of multiplying x times y. I have some way of multiplying elements. How's our time? We should stop in a minute or two, right? I'm going to have a couple of I'll have elements that I'm going to multiply, right? And I want to see what rules I need, right? So here I have x and y, and now I have x times y, and then I'm going to multiply by x again, x times y times x. And over here I just get x. And so I need that x, oh, y times x. All right, it's simple. I'm sorry I wrote it backwards for you, but it's y times x, the way I wrote it, right? I had a y coming here, and it meant an x, y meets x, and out comes y times x. And then it did it again. It met y one more time, and so, I mean, it met x one more time, and so y multiplied by x and then multiplied by x should be equal to x. And suddenly I have my parentheses in place. So I better tell you why. Back in the AB system, what happens if I take AB and I multiply by C? And what happens if I take A and I multiply by BC? This was the 3-color system that I started with. If I take AB and I multiply by C, I get C times C, which is C. If I do it the other way, I get A times BC, and BC is A, and I get A times A, and I get A, and they're not equal. So these systems are not associative. Even the simple discrimination system. So way down at the bottom of things where you're just beginning to discriminate, non-associativity comes up. It actually does, as you see. And so I'm assuming that I have some possibly non-associative multiplication like that. And then let's just look at topological moves. So another simple topological move is this one. X comes around in a little curl and meets itself and comes out as XX. But this should be the same as if nothing happened. So I need x equals x. And that was the other color rule. So my 2 color rules satisfied this. And then we get to the final one, which is really very interesting and worth spending a moment on, and then we'll stop. That's the braiding again. So now I'm acting like a theorist and trying to figure out what kind of algebraic interactions do I need, right? And the last one that I have to analyze is the braiding move. And I need that what comes out at the bottom should be the same in both cases. Now what happens here? Z goes all the way down. I have to learn to draw Z upside down, and Z goes all the way down. So that's fine. Y meets Z, so I get Y meeting Z, and that's YZ. And Y meets Z, and that's YZ, so that's okay. But the other one is a little different. I get X meeting Y. And then I get X meeting Y meeting Z. That's on the left-hand side. X meets Y, then it meets Z, so I get X, Y, Z. And on the other one, I get Y meets Z. I'm sorry, X meets Z in there. But the other one is Y meets Z. And then I have the interaction of Y meeting Z with X meeting Z. So I get over here, X meeting Z interacts with Y meeting Z. And so I need that X meeting Z, Y meeting Z should be equal to XY meeting Z. So not a bad algebraic rule. It says that Z distributes, right multiplication distributes over multiplication. Right? X times Y times Z is X times Z times Y times Z. And even though the system isn't associative, it does satisfy that. And our threefold discrimination one satisfies that. You check it out. If you took, for example, AB times C, you get C times C, which is C. If you take AC times BC, which is the distributed version, AC is B, BC is A, and B times A is C. So while it wasn't associative, it is distributive in the sense of this distributive law. So what you end up needing is you need something which is, it begins to look a little like laws of form, but in a kind of transformed way. Like this is a law of calling, and this is another sort of law of calling, XX equals X. In this case, it's more like a law of crossing, XX disappeared. So you could think of this as a calling, a crossing. And it is a crossing. You went under and then you went under again. And this is a kind of law of calling. And then there's this kind of transposition law. And then you're in topology. So you walked upward this way from laws of form ideas into really quite complex topology of knots and links and braids. And those algebras are called peculiarly quandles, algebras that satisfy those axioms. They were called quandles by the graduate student who discovered them in 1979 named David Joyce. And maybe he was reading James Joyce, I'm not sure, but anyway, he called them quandles. So that's a different line into topology and into development of algebras. But the theme that I'm interested in is starting with some elementary ideas, either mathematical or physical, and then seeing how they interrelate with developing other mathematical structures like algebra. And in the case of the quaternions and the octonions, we have this belt interpretation of quaternions, and there is also an interesting belt interpretation of octonions, for which you can look at this slideshow or talk to me at another point. But I was going to do that, but I ended up, because of your question, talking about something else that was on my mind. By the way, we ran into self-reference again here in the sense of the little curl that comes back on itself. So I like the question of where does self-reference enter when you're looking at these sorts of things. Of course, it enters in lots of places and in lots of ways. Stop there.
I think it's been a very interactive session, so I don't think we need any questions. I think there was already answered enough as he's gone along. But obviously he'll chat to people. We're going to have a 10-minute break now because I think we need to try and get the Zoom.
Just want to make sure you got on camera because
Yeah.
it was a blank screen.
Thanks very much. Right, so we need to stop recording.
First of, most importantly, Sydney, did he answer your question?
Yes, he answered.
Okay. Thank you. Thank you. It was definitely for a while, there was nothing but, you hear the voice, but you didn't see any. So, your, tablets and what have you.
Video thing.
Thank you.
Thanks. This is a valuable, I was trying to get all this on camera, but I don't know if they saw this on camera.
I got
I
to
saw
talk to,
recording.
oh, yeah, I'm trying.
Okay.
You want to stop recording? now?
Yeah. Oh, I've already done that, I think, I thought, the idea is start recording.
I guess we ought to give this back.